Okay. Okay. So going all the way back to like chapter 1, what type of property is density?
Intensive?
Intensive. What does that mean? What does it mean to be an intensive property?
It doesn't
Matters.
Yeah, so it's independent of the amount present. So does it matter if you have 1 gold nugget or 3 pounds of gold? The density of gold is all going to be the same. For which of the following can composition vary? Homogeneous mixture, homogeneous and heterogeneous mixtures, pure substance, or element?
Is it C?
It's not, but you're not wrong.
Is it B?
It's B. So what is a mixture?
2 substances that are
Right.
together.
So what's the difference between homogeneous and heterogeneous?
Homo is really like you can't separate it.
Yeah.
And then hetero is like where you can pick out the things like mud or something. You can pick out, like rocks and dirt and all that stuff.
Yeah. So homogeneous, there's different parts in it, but you can't visibly see it. So like pre-bottled Gatorade, there's a bunch going on in there, but it all looks exactly the same. Whereas heterogeneous,
Like a salad.
A salad?
Yeah, you have like croutons and olives and you can easily pick those out.
That works, yeah. Or even like a salad dressing, one of those oil-based salad dressings, and you have like the little flecks of like seasoning in it, and then the oil separates. Okay. Elements in the same group of the periodic table typically have similar chemical and physical properties, chemical properties only, mass numbers, atomic masses, or physical properties only.
Is it A?
Yes. They're going to have similar chemical and physical properties. Because in a lot of ways, chemical properties sort of relate to physical properties, like water in a gaseous state versus water in a liquid state isn't going to have, they're not going to have the same properties as each other. Name the following group. So on the periodic table, what is group 1A?
Alkali.
Alkali metals.
Alkali metals. What about group 2?
Earth, alkaline metals.
Alkaline earth. Group 6.
Is that the one that starts with the H?
No.
That's 7 is halogens.
Does this start with a C?
Yes. The chalcogens, however you want to say it. Okay, what about 7?
Halogens.
That's the halogens. And finally 8.
Noble gases.
Noble gases. Okay. Find the atomic weight for magnesium given that, excuse me, magnesium 24 weighs 23.98504 atomic mass units with a natural abundance of 78.99%. Magnesium 25 weighs 24.98584 AMU with a natural abundance of 10%. and magnesium 26 weighs 24.98259 atomic mass units with a natural abundance of 11.01%. Okay. How do we do this problem?
You like multiply the percents times the weight, and then you like add up all the weights together and divide it by 3.
So
We're
the
almost right.
percents automatically change to grams because it's magic, right?
No, you move the decimal over.
The magic is empirical formula.
Oh, okay.
Yeah. And Emma, you were so close to being right, but we're not going to divide by 3. By turning these percents into decimals and multiplying them, you're kind of like removing that step. So we're going to find a weighted average. And for a lot of classes, this is how your grade is calculated, unless you have a professor that's like, here are 3 exams, that's it, that's your grade. Really terrible experience, but some people do that. So we're going to take the weights and multiply them by their respective percentages. So someone start doing math while I'm typing all this out. And when you're writing it out, it's safe to keep all of your significant figures. So while you could just write this one as just like 0.1, you may get tripped up in significant figures when like finishing out your answer. So just sort of keep track of those. Okay.
I got 24.1949. Do you want me to keep rounding?
Yes, how many significant figures should our answer have?
4.
4. So what would that be in 4 significant figures?
24.19.
And you can do grams per mole or AMU, it's like the same thing. So basically whenever you look at a periodic table and you see all of the masses underneath the elements, this is what you're looking at, is this weighted average of all the different isotopes of that element that exist. So what is the percentage by mass of carbon? And this is octane, CaH18. How are we going to do this?
Don't we find the mass of the carbon and the hydrogen, add those together and put the carbon on top?
Yes.
Divide.
So we're going to want to find the molar mass of this entire molecule. So carbon is 12.01, right?
Yep.
And we have 8 of those. And hydrogen is 1.01. We have 18 of those. So what's our total for carbon?
96.088.
And for hydrogen? Isn't that like 18.18? Cool. Okay. So remember that a percentage is part divided by whole, and we're looking for carbon. So 96.088 is our part, and our whole is those two numbers added together. And what are those two numbers added together?
$114.23.
Okay. And when you divide all that up, what is it?
.84 09.
This is
84.11%.
okay. Yeah. So that beginning was right, but 11.
I rounded, sorry. I rounded beforehand because I only heard what you said, but I didn't look.
No, you're good. You're good. Yeah. Okay.
Would it be 84.12 or would you not round up?
I do have 84.12 on my key, but I didn't like calculate it just then, so I was just rolling with whatever you guys said, truthfully. But yeah. Okay. The molar mass of a compound is 90.08 grams per mole. Determine the molecular formula of this compound if it has an empirical formula of CH2O. Okay. So even though we haven't done like the empirical formula portion of this, it's just been given to us. Once we have empirical formula, how do we get to molecular formula?
Did you plug in the number for the amount?
What was that?
Don't you plug in some number?
Don't you divide 90.08 divided by the molar mass of the empirical formula?
Yes. So what is the molar mass of the empirical formula?
$29.01.
I think you left out a hydrogen.
30.0.
I got 30.03.
Yeah, I think you just
Yeah,
left
I
out the
did.
hydrogen. Okay, cool. So 30.03 grams per mole for the empirical formula. So now what are we going to do? Oh, wait, you already said that. Just kidding. Divide. 90.08 divided by 30.03 is equal to what?
3.
3. So what do we do with that 3?
Multiply.
Multiply each one.
So we're going to end up with C3H6O3, and that's your answer. Okay. How many grams of calcium hydroxide will be produced if 64.5 grams of water is reacted with calcium carbide? So what kind of problem is this?
Limiting reactant.
Not quite. I do have a limiting reactant problem on here, right here. So limiting reactant, you're going to know it's limiting reactant when you're given values or like amounts for both of the reactants. But if it's just one, we're basically just looking for theoretical yield. So we're sort of assuming that water is our limiting reactant, we have an excess of calcium carbide, or that we have just enough of both. So, oh shoot, what was that formula? See. Okay. We have 64.5 grams of water. Where are we gonna go?
Find the mass of that.
Molar mass of water, which is 18.02. And what's gonna go on top?
1 mole.
1 mole of water.
And then 2 moles H2O would go on the bottom. And then 1 mole CaOH2. And then you do the 1 mole on the bottom and then get molar mass.
Okay, I did 6 grams. And what's the molar mass of calcium hydroxide?
Is it 74.09?
Yes. And so we work all that out, and how many grams of calcium hydroxide do we produce?
$530.41. Or would you just do 530?
Let me go through this. Something went wrong somewhere.
Is it 132?
Yes.
Yeah, I got 132.
So because of sig figs, I'm gonna bump it up to 133. Okay. So we have 133. So if you run this experiment in a lab and you end up with 108 grams of calcium hydroxide, what's your percent yield?
Is this where you do part over whole
Mm-hmm.
times 100?
Yes.
Okay.
Well, in this case, like, yeah, it's part over whole, but in this case, it's actual over theoretical. So this up here is our theoretical yield. This is what we should get if everything goes absolutely perfect and nothing escapes, but that's not how like labs work. So you inevitably end up with less than like you should. So yeah.
0.812.
So 81.2%. Okay. How many grams of magnesium bromide are produced when 777 milliliters of a 0.987 molar magnesium reacts with 654 milliliters of 0.250 molar bromine?
Oof.
And what is the limiting reagent? So in a limiting reagent problem, we're going to have to like figure out the theoretical yield of both. And how do we determine which one is our limiting reagent?
You divide it by the number of moles each one has.
Whichever one has the least amount of moles.
Yeah, whichever one produces the least amount. So here I've given you milliliters and molarity. Where are we going to go from milliliters and molarity?
Volume. Or
Convert to liters, then multiply each to get the moles.
Yes. So 0.987 times 777. Okay. So how many moles of magnesium do we have?
Zero 0.767.
Just for the sake of like accuracy, I like to keep all like my calculator numbers until I'm completely done with the problem. Oh my god, that looks terrible. And what about for bromine?
0.1635.
Yes. So now what are we going to do with these?
Divide each by the lowest one.
Not, so that's going to be empirical. For this, we're going to have to, since we're trying to find the limiting reagent, we have to take each of them into product. So the formula for this is Mg plus Br2 goes to and then NA2. So let's start with magnesium, 0.766899 moles magnesium. What goes on bottom?
Oh. 2 moles.
Magnesium. And what goes on top?
It would be 1 mole bromine.
So,
Or would it go to grams?
So what are we ultimately trying to get to?
Liters.
grams of magnesium bromide.
Right. So now we're in moles of magnesium. So what should we go to?
Moles of magnesium bromide.
Moles of magnesium bromide. Oh. And then we're going to go into grams. So you can put everything into moles and then decide like which is the limiting reagent and then take that into grams. I typically just do it while I'm here, like that just makes sense for me. So that once I'm done, like I'm done. So 1 mole of magnesium bromide. What is the molar mass of magnesium bromide?
Sorry, this is probably like a really stupid question, but why did you give bromide in the beginning a 2? Shouldn't the magnesium had a 2? Or I'm kind of confused on the placement.
So remember the diatomic molecules?
Yeah, I know how they're supposed to, how would you know is a diatomic molecule?
So Hoffenbrinkel.
So whenever it's just one of those, you just assume?
Whenever it's one of these on their own, they're going to form a diatomic molecule with another one.
Okay.
Aren't you supposed to use the limiting reagent for the moles thing?
So this is helping us determine what the limiting reagent is.
Oh, okay.
So yeah, honestly, I'm gonna grab a fresh thingy. Okay. So 0.76689 moles of magnesium goes to 2 moles. And so what's the molar mass of magnesium bromide?
104.209. Oh, I forgot to add, there's 2 BRs.
Yeah, sorry, that's my fault. I forgot to write that out when I first wrote the equation.
So it'd be 184.113.
So how many grams of magnesium bromide does this produce?
Be 141.20.
Okay. And then we had 0.1635 moles of bromine. Bromide. So what's going to go down here?
One mole.
1 mole. So 1 mole of bromide goes to what?
2 moles of magnesium bromide.
2 moles
To
of
1
magnesium.
mole of magnesium bromide.
much is produced from this?
$60.20.
Yes. So what's the limiting reactant?
Bromide.
Bromide. Oh my God. Why didn't anyone call me out on this? I totally learned everything. This should be a 1. That's fine because bromide is still like the limiting reactant. It's just our amount changes. So if we take away the fact that we multiplied everything by 2, we just half this and like it's good. The answer is 30.2 grams. I'm sorry, y'all.
Wait, but that's not balanced. Unless you take away the 2 from the other magnesium.
It was balanced this whole time. Oh my God. Is anyone else ready for the semester to be over? I'm so ready.
Yes.
Yes.
I'm like so brain dead. All my professors, like, they weren't doing like the whole live Zoom thing. They were like, here's everything, just do it as you want. So I left everything for today. So I've been up since like 8 a.m.
Oh, mood.
I had a paper due Sunday.
Oh, a Sunday? It's like the worst day.
Let's get
So 30.2 grams are produced and bromide is the limiting reagent. Okay, which ions are always soluble no matter what?
NO3.
Great.
Nitrates, NO3. And what's the other one?
Ammonia.
Ammonium. Okay, how many moles of iodine ion are present in 0.2 liters of a 0.4 molar solution of cobalt iodide? Sorry, cobalt 2 iodide. So this is kind of like what we just did, but a lot simpler. So we have 0.2 liters and 0.4, right? Yeah, 0.4 molar. So how many moles of cobalt iodide do we have?
Zero 0.08.
0.08. And we're going to keep these sig figs, so 0, 0, but yes, it's the same exact. Moles of cobalt 2 iodide. So how are we going to find the number of cobalt ions, or sorry, iodide ions?
You go from moles of the cobalt iodide to just iodide?
Yeah. So what we have to do is we have to break up this compound, right? So cobalt 2 plus comes together with iodide minus to make cobalt. We have this 2 here, so there has to be a 2 here. So now we can do that, right?
Yes.
So 0.0800 moles cobalt 2 iodide. Cobalt 2 iodide. do we have?
Zero 0.16.
Yes. Okay. The valence shell of the element X contains 2 electrons in a 5s subshell. Below that shell, element X has a partially filled 4d subshell. What type of element is X? So let's start with this valence shell, the 5s. How many electrons can a 5s shell, or how many valence electrons can an s shell hold?
2.
2.
2. And this element has 2. It has a completely filled 5s shell. But 4d is only partially filled. So where does d put us?
In the transition.
It's a transition metal. So the reason that the numbers work like that, if you'll remember, once you hit D, that energy level lags by 1, as opposed to where the 5 and the S are, or the S and the P are. Okay. Which electron configuration represents a violation of the Pauli exclusion principle? It's not really a way for me to like word this.
It's B.
It is not.
B and
That's
E.
not right. B is not right, but
C.
it's C.
There's
C is
two.
the answer. So,
Oh,
I mean, really, B is the only one. No. A is the only one that is right. That is like a good one. B, C, and D, or sorry, B, D, and E all have things wrong with them, but it doesn't directly violate this principle. So what does the Pauli exclusion principle state?
They
can't have the same quantum numbers.
No 2 electrons can have the exact same quantum numbers within the same atom. But you notice in C, you have 2 upwards facing arrows within the same shell, within the same like little region. That means they're both going to have a plus 1/2 at the end, and that is not possible because they're going to have, those first 3 numbers are going to be the same. If this weren't a violation, those first 3 numbers would still be the same, and then one would have a plus 1/2, the other would have a minus 1/2. Okay, the n equals 1 shell contains blank p orbitals. All the other shells contain blank p orbitals. How many p orbitals does the first energy level have?
0.
0. Doesn't have any. How many p orbitals do the rest have?
1. Or a lot more.
3.
3. Okay. In which set of elements would all members be expected to have very similar chemical properties? You can observe. I'm going to go ahead and grab mine.
Is it E?
It is E. Yes. Okay. Atomic radius generally decreases as we move down a group from right down a group and from right to left across a period, up a group and from right to left across a period, down a group, the period position has no effect, down a group and from left to right across a period, up a group and from left to right across a period.
Is it A?
It is not.
E.
It's
It
down
is-
a group, and it's from right to left.
It
Wait,
is E.
E, right?
It's E.
oh, it decreases. Okay.
So, yeah. Okay. Blank have the lowest first ionization energies of the groups listed. The alkaline earth metals, alkali metals, halogens, transition elements, or noble gases.
The B.
It is the alkali metals. Just a warning, I have like several questions over periodic trends because last class I noticed she mentioned that a lot of people got those questions wrong on those exams and quizzes and whatever you guys had over it. So I made sure to like touch all bases. Which of the following is an isoelectronic series? First off, what is an isoelectronic series?
Where you're trying to get like all elements to equal another element.
Yes, they're all going to have the same number of electrons.
Is this C? Wait, no, that's wrong. Never mind. Never mind.
Is it E?
It is E. So these all of the ones that aren't neon have been made to equal neon. Yep. Okay, which isoelectronic series is correctly arranged in order of increasing radius? So, okay, let's narrow this down. What type of radius are we looking at? Atomic or ionic?
Is it ionic?
Yes, we're looking at ionic radii. So, generally speaking, is a positive ion going to be bigger or smaller than a negative ion?
Smaller.
Yes,
So would it be C?
it's C.
Okay, that's like that.
Okay. In general, as you go across a period in the periodic table from left to right, the atomic radius either increases or decreases. The electron affinity becomes increasingly or decreasingly negative, and the first ionization energy either increases or decreases. So as you go from left to right, does atomic radius increase or decrease?
Decrease.
It decreases. So what about electron affinity? Does it become more or less negative?
More? Is it more negative?
Becomes more negative. It becomes increasingly negative. And does the first ionization energy increase or decrease?
Increase?
Increase. So what's the answer?
B.
B. So I would really highly recommend you guys still have like the sheet that has all like the trends and stuff laid out on it. Have it in front of you when you take your exam. Like, my biggest advice, since it's like online and you are able to use resources, is just make sure you have everything before you start, so you're not wasting time like running around your room or rummaging through your bag trying to find something. Like, just have it all laid out like nice and neat, separated by like chapter or topic, and that way you can just go in and get things done really quickly. Okay,
But not quickly.
not too quickly. Correct. When I took my first like online exam after this transition, I like blew through it. I spent like 20 minutes on it. I was like, man, that was so easy. And I made like a 72 on it. So like, don't do that. Okay. The blank have the most negative electron affinities: halogens, chalcogens, alkali metals, transition metals, or alkaline earth metals.
Is it halogen?
Halogens. So remember that these halogens are really, really reactive. They really want another electron. So they're going to have the strongest affinity for another electron because they really want it. They're so close. Okay. Find the enthalpy of reaction for the following. Is this endothermic or exothermic? So how do we work out this problem? It's been a while.
I think you add up the products, the enthalpy of products, and then you subtract it by the sum of the reactants.
Yeah, so we're going to subtract the reactants from the products. And yeah, the products are going to come first. So we have one of this first one, this like calcium, whatever this is, I have no idea. And so we're going to put the value that they give us into the equation. I'm going to do this. We're going to add that together with, so like the like proper like way of stating this formula is bonds formed minus bonds broken, because we're breaking the reactant bonds to form the product bonds. And then water, we have 2, and that's negative 627.3. And we're going to subtract reactants from it. 1, and then 972.7 plus 2. Then you do math. And what's the answer? Anyone can answer.
Negative 91,044. Wait, negative 9,144.5.
I got negative 6,665.2. We love math.
Okay, so let's kind of break this down. So in this first portion, where is it?
I got negative 6,129.7.
Yes.
Yeah, so did I.
Yes.
Yeah, I don't know where I went wrong.
So my strongest recommendation in doing this is to like have a sheet of paper, like scratch paper, to really like write everything out. And what I do is I really hate calculators. Anytime I know people that will just like put this entire thing in their calculator and like get the right answer, and I'm not that person. I can't do that. It just doesn't do it for me. I don't know what I do wrong. So I break these up. So I'll do the multiplication and I'll rewrite everything out. And then I'll do the addition within these brackets. And then I'll write that minus whatever this addition is. And then I'll subtract. I do everything a really long way. And in the end, maybe it leaves more room for error, but I don't know. It just always works out better for me than just like typing everything in. Okay. Write out a complete set of quantum numbers for the last electron in the halogen in the third period. So
Wait,
what's
so
that?
it would be exothermic or
Oh,
endothermic?
shoot. Yes, sorry. It is exothermic. Sorry. It is exothermic. Okay. Write a complete set of quantum numbers for the last electron and the halogen in the third period. So what is that halogen?
Chlorine?
Chlorine.
P4.
So what is our N quantum number?
Four.
No,
Isn't it 2?
3.
it's 3. Yeah, it's 3. L, right? It's L. I can't remember the letter for that one. Yeah, okay, cool. What is our L number?
1.
1. What about M sub L?
One.
Is 1.
Mm,
Is it 2?
No, because P only has the 3. It's negative 1, 0, and 1.
So it would be +1.
Yeah. Because it's the last. It's the last one.
Because it's 3.
let's draw this out. So we have, okay. So we have the 3, 0 plus 1 minus 1, right? So how many valence electrons do we have in chlorine?
5.
7.
7. Our noble gases, we have 7 valence electrons. So remember how we write these in. 1, 2, 3, 4. This isn't right.
I thought there was only 5 valence electrons. 3, 4, 5. It's in the P series. Aren't you just counting the last?
Yeah, shoot.
So it'd be 5, so ML would be 0.
Yes. Yes, sorry.
And then MS is your choice, right? Or would it be +1? Or +1/2? Or -1/2?
Yeah, the MS is your choice. When I did this question on my exam, I wrote the arrow facing upwards, and then I wrote a -1/2, and she still gave me credit, so. Yeah, sorry. M sub L is 0. And finally, M sub S is your choice, plus or minus 1/2.
All I can see is silver.
Okay. What is this frequency of light that has a wavelength of 2.25 times 10 to the -5 meters? So what is our formula?
C equals wavelength times frequency.
Yes. So C is 2.99 times 10 to the 8th. Is equal to, we have our wavelength of 2.25 times 10 to the -5. And we're looking for frequency. So you do math and then you figure out the frequency and what is it?
Wow.
1.33 e to the 13.
Yes. .33 times 10 to the 13th inverse seconds. So I'm going to write it as 1/s, but you can write it as the negative subscript or superscript, sorry. Okay. Elements from opposite sides of the periodic table tend to form what type of compounds?
Ionic.
Ionic compounds. In the molecule, okay. So I wrote this one out because like I couldn't find a picture of it. But basically what I mean by this is C which of these elements has the largest partial negative charge?
Fluorine.
Fluorine. So how do we determine what has a negative charge, a partial negative charge?
The table.
Yes. So we base this off of, is it a polar bond or is it not? If it's a polar bond, we're going to have a partial negative charge on one of them and a partial positive on the other. But the way that we determine if an element is, or if a bond is polar or not, is based on the difference in electronegativity. And we determine the difference in electronegativity based on where they are in relation to each other on the periodic table. So if you remember going through the chapter talking about periodic trends, fluorine is the most electronegative element like ever. So if it's attached to anything, it has a partial negative charge. Okay. The molecular geometry of the SF2 molecule is, so in order to do this, we need to draw out the Lewis structure. So we have SF2. Sulfur has 6, 7. So okay. So what's the molecular geometry?
Tetrahedral.
That is the electron domain geometry, but that is right.
Bent.
Bent.
Oh, okay.
But yeah, for the full geometry, it would be tetrahedral bent. Okay. An ideal gas differs from a real gas in that the molecule of an ideal gas, molecules, that should be molecules of an ideal gas, have no attraction for one another, have no appreciable molecular volumes, have an average molecular mass, have a molecular weight of 0, or have no kinetic energy.
Is it D?
It is not D. Part of the reason I put
it
this
C?
one, it is not C either. So part of the reason I put this one on here was because it's one that I got wrong on this exam that I took. This is a question I pulled from a past exam. And like, I'm gonna be totally honest, it still kind of messes me up and I don't fully understand it, but I know the answer. And
Is it B?
no,
Is it E?
no,
A.
it's A. They have no attraction for each other, which is a really weird concept,
Makes
but
sense.
that's why it's ideal, because it really doesn't exist. We can get real gases to behave similar to that of an ideal gas, but we're never going to reach that standard because chemical and energetic attractions are just always going to exist. Like, they just happen. Like, the best way I can think of to describe this is if you've ever taken like a physics class, even like in high school, and you just sort of like disregard the fact that friction exists for like 90% of the problems you do, like in high school, because you're just taking it because you have to. And yeah, that's the best way I can think of. It's kind of like in an ideal gas, we're just like, this messes with our formula, so we're just gonna like forget, like pretend it doesn't exist. Okay, when sodium chloride dissolves in water, aqueous sodium ions and chloride ions result. The force of attraction between sodium ion and water is called a blank interaction. Is it ion-ion, London dispersion force, excuse me, hydrogen bonding, ion dipole, or dipole-dipole?
Ion-ion?
Half yes.
London dispersion as well, isn't it?
Yes, London dispersion is going to be in everything. But ion dipole, which is a really weird one. I feel like you guys didn't like talk about it much. But yeah, so a dipole is a momentary charge on one end of an atom or a molecule. So we've talked about before in class the fact that water is a polar molecule, and that's very important, like in the body and biological processes. So because it's polar, it has a positive end and a negative end. That central oxygen has a negative charge. And this positive sodium charge is going to be attracted to that. And that's what's going to cause them to like stick together. Okay, what does the phrase like dissolves like mean?
Polar will dissolve in polar, and non-polar will dissolve in non-polar.
Yes, exactly. Polar solvents dissolve non-polar, or no, polar solvents dissolve polar solutes. And non-polar solvents dissolve non-polar solutes. So if you're unlucky enough to have to take organic chemistry, first of all, sorry, it's not fun. It's not a fun time, but you can do it. But you do this lab, which was like my favorite lab ever because it was really quick. And like, if you think like your current chemistry labs are long, like just wait. But there's a chromatography lab where you put these unknowns on a sheet and you set them in this deal and they travel up, and you determine which one of them are polar and which are non-polar and which are weakly polar based on how far they traveled, because the plate they're on is non-polar, but the solvent they're in is polar. So yeah. And honestly, that one was quite a good time. I enjoyed it. Okay. In a saturated solution of a salt and a water, the rate of crystallization is greater than the rate of dissolution. The rate of dissolution is greater than the rate of crystallization. The rate of crystallization and rate of dissolution are equal. Addition of more water causes massive crystallization, or seed crystal addition may cause massive crystallization.
E.
No. Wait, what'd you say? You said E?
Yeah.
Okay, yeah, no.
B?
Not B.
Is it D?
It is not D.
Is it A?
It is not A.
Is it C?
It's C.
I don't get chapter 11, man. I did not get it at all.
Speak louder for the people in the back.
I will say chapter 11 definitely ventures into Chem 2.
Whoa.
Yeah, sorry. Personally, I really didn't like Chem 2. It doesn't make as much sense to me as this stuff does. So getting into these topics is like, But, so if you have a saturated solution, so like, let's say your throat really hurts, you're about to gargle some salt water, try and help it out. So you kind of don't know you have a saturated solution until you ruin it. A saturated solution is when it is at its max capacity and you're not going to see like salt collecting at the bottom. But you're not going to know that it's at its max capacity until you add salt and it doesn't dissolve, right?
Okay.
So in this, it's kind of like a treadmill effect of like I'm forming crystals just as fast as I'm dissolving them, so you never see it. Does that kind of make sense?
I guess.
Because like if you were to take table salt, for example, so it dissolves in the water, right? Like we talked about up here. So you have sodium ions and chloride ions just sort of floating around. Well, occasionally they're going to bump into each other and they're going to form, but then just as quickly they're going to break off and go their own way. Does that make sense?
Mhm.
Okay.